All right. This is a higher frequency tuning fork, which means it vibrates back and forth at a higher rate, which means that the wave does not have a chance to move as far as it does with the 256. So we should have a shorter wavelength.
So do you have to do like a calculation of
Yeah, we have to do that calculation. Instead of 340 over 256, it's 340 over 512. So the wavelength is the speed divided by the frequency. That's hertz, and that's meters per second. Point what?
Yeah, 661.
Units?
Hertz.
Remember, a hertz is a 1 over second, so I have a meter per second divided by hertz, which is a meter per second divided by 1 over seconds, which is a meter per second times seconds over 1. And I want just meters. All right, so I have a wavelength of 0.664 meters. The first harmonic, well, the first harmonic should be a quarter of that. So L1 would be 1/4 of the wavelength. And L3 should be the 3/4 of the wavelength. So a quarter of this.
166 meters.
166.
Yes, sir.
And then 3/4 of that.
4.498.
All right. So the first one about 16.6. So on here it should be somewhere around that spot right there. Now we should not have enough water in there at the moment. So let's add some. And the tuning fork here. Mike must be having sound issues today with me. Too far here. So below, go up to it. All right, 100th time is the charm. Oh, actually, this worked better. Definitely heard that one. So, looking through there, it looks like it was at 14 centimeters plus the 2, so 16 centimeters. And so this was our predicted and our experimental 0.160 meters. So again, not bad. All right, the next harmonic, the one that caused us to go down this journey, caused me to go down this journey and drag you along with me, is that next harmonic, which should be at roughly 1/2 meter. So on here, it would be, that's 50 right there, so it should be somewhere around here. definitely heard that. Try that one again. Somewhere around where I expected. So it looks like about 47.6. Plus the 2. So we predicted that and ended up getting 0.496 meters. There seems to be some legitimacy to the stuff I'm talking to you about. Now, I don't know if you heard it when it was going down, as we were getting closer to that, when we passed by about the 40 centimeter mark, the sound changed slightly. Some students confuse that with a harmonic. And so this is one of the, although legitimately you shouldn't do this, as far as science is concerned, but in this lab, it's okay to look to see what your prediction is, just so you can rule out the false ones. Now, in the original version of a lab dealing with that, if you got the first one off, then you got the third one off, and you got the fifth one off, and you got the seventh one off, and it ended up just results were, you're shooting for a speed of sound around 340 meters per second, you're getting around 200 meters per second, because you misidentified that first harmonic. Let's see if we can find a few false harmonics. That's a false one. Slight sound there, that was also a false one. That's the real first harmonic. So just because you'll hear the sound go up and then down again, when you get to the first harmonic, that is going to be the loudest of all of it. Questions? Okay, the last bit, I think it's going to be the last bit, is let's talk about the Doppler effect. Imagine there's a very still pond. You take a small little pebble and you throw the pebble into the pond and it goes poof, and you get this wave sort of going out from that. So you hit it right there, and then a moment later you get this ripple that's centered at that spot. So this is another moment at a time. So it's rippling out and then ripple out farther. And so these are 3 moments in time. When this wave gets to here, so when that first wave that is going out like that, when it gets to this point, what happens is that you throw another rock, and because you are that good, you put that second rock in the exact same spot as the first rock, so you start a second set of waves there. And then some time later, that wave is now this big. So you get these crests of waves that are hitting you. So if you're a bug on the water right here, and a bug on the water over here, those famous 4-legged bugs, you're going to get hit by the waves. It's as frequent. This one will be hit by the waves as frequently as that one will be hit by the waves. So, from a sound point of view, the frequency is the same on both sides. However, in scenario number 2, You throw a rock into the water, it sends out a wave, and then it sends out a bigger wave. Well, and then that wave gets bigger. Now, the amplitude gets smaller because as you spread out, there's the same amount of water spread out over a much larger area. But the second rock you throw this time is not in the exact same spot, but forward a little bit. So you throw the second rock here. Now the second waves that are going to be sent out are centered around this point, and so that second wave will be closer to one side than the other. So if you're a bug on the water, which one will feel the waves more frequently? And so he will perceive a higher frequency than he does. And in terms of sound, if the thing that's making the sound or making the waves is coming towards you, you will hear a higher frequency than if it's going away from you. Now, a note for the purists in the group. It said you will hear a higher frequency. Officially, you'd hear a higher pitch. Frequency is related to pitch. I use frequency and pitch interchangeably. I haven't seen a reason not to, but I know officially you actually hear a pitch caused by a certain frequency of sound, but I will use them interchangeably. All right, so as this is getting closer to it, the waves are going to hit more frequently. So the wavelength is smaller than over here. Wavelength being that's a peak to peak distance. So higher frequency, shorter wavelength. But the wave is still moving at the speed of whatever the speed of sound, or in case of this, the speed that they can travel across the water. All right, questions to hear? Now in terms of sound, think of this ridge right here as high pressure. So if I make a sound, I'll have points where the air molecules are really close to each other. And again, for the purists, I know that really it's not such a thing as an air molecule. Air molecule is composed of many different other molecules. Hopefully go with the spirit of. When I say air molecule, I mean molecules in the air. So I get a whole bunch of them close to each other. That's a high pressure point. And then I get points which are farther apart. So this is compression and rarefaction. Spelled like rarefaction, but I've always heard it pronounced rarefaction. And then again, high pressure again. So if I drew this in this manner right here, or if I drew it in the sort of the sine wave look, I'd have high pressure here, I'd have low pressure, I'd have high pressure, low pressure. So that's what it would look like from a side point of view. Or if I drew it with my circle diagram, I'd have a line there and a line there where I've got the peaks, and then in between is the rarefaction. So this represents the higher pressure. In the case of the water, the peak of the actual wave. In terms of sound, it's where the highest pressure is hitting you. All right, scenario number 3. I throw my still pond, got the rock, I throw it, and that sound gets bigger and bigger. The next rock I throw is, oh, yes, sorry, Grace?
What does rarefaction mean exactly? Like, how's that defined?
Wow, never actually had to define it. So compression is the point where particles are much closer to each other. Rarefaction would be a point or a locale where the particles are farther apart from each other when talking about a gas.
Is that why your ears pop in an airplane? Because you're under high pressure, then all of a sudden you're under low pressure as you go up?
Generally, I hear rarefaction used in combination with, so sound is high pressure, low pressure, high pressure. It's the low pressure part of the pattern that's hitting your ear. In terms of a plane, I guess you could consider it rarefaction, but typically I've only seen it in context of noise or sound. and not in the general ambient pressure. So I'm fine with saying that's caused by rarefaction. The purist might say something different. Is that sufficient?
Yeah.
Okay. Other questions? And anyone need me to go back to the previous screen? All right, the next rock you throw is outside of this. So you throw that rock there. And then that will expand. So the question is, what's happening there? What's happening where they overlap?
Pressure is built up between both of them.
And say it again?
Like more pressure is built up between the both of them?
Yep.
In that area?
What kind of interference is that called?
Constructive.
Yep, it is constructive interference. So we have these two higher pressures now on top of each other, and you would add them. It's called principle of superposition, which I believe was the word I was looking for the other day. I couldn't quite remember. So you have this superposition going on. You basically add them together, and you get even higher pressure than you had before. Now, if you did this consistently, what you would end up with is you have that first wave here, and then you have another wave, and then another wave, and then another wave, and so on. You end up with sort of a cone here. Now, I've drawn it where they're separated farther apart, but if this thing's making 400 waves a second, so 400 hertz, then these are much closer to each other, but you get this cone here of high pressure. Now, if you are standing on the ground, when this hits you, what would you hear?
Would it be like a high pitch?
No, it's not a frequency issue.
A higher volume controlling the rest.
And what do we call that higher volume?
Higher frequency.
No, not higher frequency. It is indeed a higher volume because you got more pressure, and right behind it you'd have a bigger rarefaction, so you get hit by even more and then less. In this situation, it's known as a sonic boom. And that's the sonic boom. Now, it's very difficult to create a sonic boom, and also, I mean, if I clap my hand, we have, my hands get closer together, it forces air out very quickly when my hands actually touch, and so we get this big thing of pressure going out. That's not a sonic boom because I'm smacking two things together. You create a sonic boom by having something move faster than the speed of sound. So if I took a whip and I was cracking it, the whip is just slicing through the air, it doesn't have to hit anything, and better if it doesn't. If the whip is slicing through the air, it's pushing air molecules out of the way. If it's moving faster than the air molecules can move, because that basically limits the speed of sound, is how fast the air molecules can move. If it's going faster than the air molecules can move, you get this buildup of pressure and you get the pop of a cracked whip. Come on. Get past the ad.
Illegal.
The Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the